1. Operating system definition core functions. As iOS is a system software that manages hardware, resources, CPU, memory devices, and software operations. Strong hardware management, processor scheduling allocates CPU time via algorithms, memory control manages RAM allocates protection using gaining segmentation, device control, coordinate procedures via drivers, printers, storage, file systems organize data hierarchy with metadata FAT induce and across premises software environment, provides system call interface for applications, manages software lifecycle installation updates, maintains stability, strong selection. 1B. Key resource management functions, key mechanisms, process management, scheduling algorithms, semaphores, prevent conflicts, optimize CPU, memory management, purging memory protection, prevent leaks, and moodwise across file management, hierarchical countries, permissions, secure data organization, device management, driver protocols across queues, hardware, software deletion, significance, optimizes resource utilization, CPU memory issues, system stability where processed memory enhances UX, strong GUIs, and organized file access.
Today, we will explore the evolution of computer systems, how they transform from basic base processor to powerful AI-driven platforms. Let's dive in. Evolution of OS, 1950s to present. Early mainframes, 1950s to 1960s. In the early days, computers can jobs in bases, meaning no user interaction. They were also single tasking, so only one program run at a time. Time sharing, 1960 to 1970s. Then came time sharing, allowing multiple users to access a single machine. Systems like CTSS and Multics paved the way of modern multitasking. Personal computers. The introduction of multiprocessors led to personal computers. Early OS like CP/M, MS-DOS, and Apple OS made computers accessible to individuals. Graphical user interfaces. Then GUIs arrived. Windows, Mac OS, and Unix-based systems made computers more user-friendly, replacing text-based interfaces. Network and distributed OS. The rise of the internet led to network operating systems supporting connectivity, security, and distributed computing. Modern OS. Today we have mobile OS like Android and iOS, cloud-based platforms, and even AI-driven OS features improving security and efficiency. Section 2, Key OS milestones. Let's look at some major breakthroughs. 1960s, time sharing allowed multitasking. Virtual memory expanded usable memory. 1980s, GUIs made computers user-friendly. Networking and TCP/IP led to the Internet revolution. 1991, Linux, open source OS changed the industry. 2000s, virtualization improved server efficiency. 2020s, AI ML enhances security and optimization. Impact of hardware on OS, processor evolution. From single core to multi-core, OSs had to adapt for parallel processing and efficient scheduling. Memory and storage. Early computers relied on limited RAM, but today OSs optimize large memory and fast SSDs for better performance. Networking and cloud computing. Ethernet, Wi-Fi, and cloud computing led to virtualization and containerizations, making OSs more scalable. Graphics and AI. GPUs brought major advancements in gaming, machine learning, and AI, requiring OS support for DirectX, OpenGL, and AI acceleration. Mobile and IoT. With mobile devices and IoT, OSs needed to focus on power efficiency, security, and real-time processing. Future trends. Looking ahead, we have quantum computing, IoT, and AI-driven OSs shaping the next era of computing. And that's a quick journey through the evolution of operating systems. OSs have come a long way, and with AI, cloud, and quantum computing, the future looks even more exciting.
Interprocess communication and its role in concurrent programming. What is IPC? Interprocess communication, or IPC, is the way that processes, whether on the same machine or across different systems, talk to each other, share resources, and keep everything in sync. Why is IPC important? IPC ensures processes can communicate smoothly, share resources, avoid conflicts. Without it, we'd run into chaos in concurrent programming, where multiple tasks need to happen at the same time. Types of IPC mechanisms. Pipes. Think of these like one-way streets for data. One process writes data, another reads it. They can either be one-way or bidirectional. Sockets. These are like long-distance communication tools that let processes talk to each other even when they're on different machines. Shared memory. This is all about speed. Processes communicate directly as accessing a shared memory space. Message passing. In this method, processes send messages to each other without sharing memory, which is useful for specific communication patterns. Differences between shared memory and message passing. Shared memory. Here, multiple processes access a common memory space to communicate. It's like having a shared notebook where everyone can read and write. Message passing. In message passing, processes send messages to each other. It's a bit like sending a letter. You decide who sends and who receives. Key differences. In terms of communication, with message passing, the programmer decides who sends and who receives the data, while in shared memory, communication happens via shared variables in memory. Data distribution. In message passing, the programmer handles the distribution of data, while shared memory lets the system handle it. Hardware support. In message passing, it is quite simple. It just needs a network card. Shared memory, however, needs more complex hardware setup. In terms of speed, shared memory is faster because processes directly access the memory. Message passing, on the other hand, needs extra steps like copying data. Security. Message passing is safer because it encapsulates data, meaning processes don't directly access each other's memory. Programming complexity. Message passing is tricky because it requires careful coordination. Shared memory is simpler but still challenging when it comes to ensuring correctness. Performance. Message passing is easier to fine-tune for performance once correctness is achieved. In shared memory, however, performance is harder to optimize and might not always align with correctness. Advantages and disadvantages of using pipes for IPC in concurrent systems. Advantage of pipes. It is quite simple to implement. They are easy to use and widely supported. Streamlined communication. They are efficient when data needs to flow continuously between processes. Automatic buffering. Pipes handle data flow management automatically, so developers don't have to worry about it. Process synchronization. Pipes help keep things in order, ensuring that readers wait for writers when needed. Data integrity. They maintain the correct order of data, preventing corruption. Disadvantages of pipes. Limited scope. Pipes are mostly used for communication within the same system, so they're not great for distributed systems. Blocking behavior. If the pipe's buffer is full, the writer will have to wait, which can slow things down. Fixed buffer size. The amount of data that can be transferred at once is limited by the buffer size. Unidirectional by default. By default, the pipes only allow one-way communication. If you need a two-way communication, however, you have to do extra setup. Debugging challenges. It can be hard to track what's going on inside the pipe and diagnose issues with the data flow.
Concurrent programming and sequential programming. Concurrency in programming refers to a system capacity to manage several tasks concurrently. Tasks are broken down into smaller subtasks in concurrent programming. This makes it possible to use resources more effectively. Sequential programming, on the other hand, every task is finished before moving on into the next one. There is no overlap in the task execution, and they are completed in a precise order may not be as effective, particularly when managing activities that could be performed in parallel. So in basic terms, concurrent programming is almost the opposite of sequential programming, where concurrent means multitasking systems and sequential programming is finishing each task one by one. A race condition. A race condition is when several threads or processes access shared resources, such as variables or memories, simultaneously, and the result is contingent on the order or timing of their execution. This is known as a race condition in concurrent programming. Mutating race conditions. Race conditions occur when multiple threads processes access shared resources simultaneously. The key prevention technique techniques. One, locks or mutex allow one thread to access a resource at a time. Two, semaphores limit the number of concurrent accesses to a resource. Three, monitors combine locks and conditional variables for controlled access. Four, condition variables pause threads until specific conditions are met. Five, atomic operations ensure non-interruptible updates without locks. Six, thread local storage assign each thread its own resource instance. Synchronization in concurrent programming. Importance of synchronization in concurrent programming: ensure multiple threads process run without errors, preventing race conditions and coordinating resources access. Key concepts: mutex resurrects access to shared resources, preventing race conditions. Deadlock occurs when the threads wait indefinitely for each other's resources. Deadlock handling. The prevention of deadlock handling. Resource ordering enforce a fixed request order. No hold and wait. Release resources before requesting new ones. Avoidance. Bunkers algorithm allocates resources dynamically to maintain safety. Resource graphs detect potential deadlocks via cycle analysis. Detection and recovery. Detection regularly check for circular waits. Recovery resolved by terminating or rolling back processes.
Think of a system that uses several processes to process data simultaneously. While each process is in charge of a particular task, for each work to be completed effectively, this process must exchange data and communicate with each other. So, when choosing IPC mechanisms, we have to consider a couple of things. I went with the hybrid approach, which involves the shared memory and message queues. Shared memory enables fast data exchange by allowing process to read and write directly to a common memory space, eliminating redundant data copying. This is useful for handling large data sets. However, it requires synchronization to prevent race condition and ensure data consistency. On the other hand, we have message queues, which facilitate asynchronous communication by allowing processes to send and receive structured messages. It is ideal for small and controlled messages, event notifications, and decoupled processing. Unlike shared memory, message queues naturally prevent data inconsistencies, but have higher overhead of large data. So, the hybrid approach is very useful because shared memory effectively handles large data, while message queues ensure structured communication and synchronization, achieving a balance of speed and flexibility. And then we have to also consider the challenges of synchronization. Synchronization is critical to maintaining data integrity and preventing concurrent issues. To achieve this, I would implement mutex, which are also known as mutual exclusion locks, which prevents race condition by ensuring one process accessed shared memory at a time. A process must acquire lock before modifying data and release it afterwards. The second thing is metaphors, which regulate access to limited resources by allowing multiple processes up to a defined limit. The third one, I'd go with deadlock prevention, which implements strategies such as timeouts, lock ordering, and deadlock detection and recovery. The fourth one, I choose condition variables, which allow processes to wait for a specific condition before proceeding. For example, a worker process might wait for a signal indicating data is ready to be processed. The fifth and last one will be barrier synchronization, which ensures all processes reach a defined checkpoint before proceeding. Useful multi-phase task where intermediate results must be available before moving forward. Let's sum up everything we've covered so far today. Firstly, we'll look at the role and the importance of operating systems. Operating system manages hardware and software resources, ensuring efficient multitasking, memory allocation, and process scheduling. Features like file organization, CPU control, and device management enables seamless human-computer interaction, optimizing performance and stability. Secondly, we look at the evolution of operating systems. Operating systems development has progressed from batch processing, which started in the early 1950s, to cloud-based systems adapting to hardware advancements. Innovations like time-sharing, GUIs, and virtualization enhance capabilities, while modern operating systems handle battery efficiency and real-life constraints in mobile and embedded systems. Thirdly, we looked at inter-process communications, which we know are also called IPCs. IPCs enables efficient data exchange between processes using shared memory, which is fast but requires synchronization. Message passing, which is reliable for distributed systems but has a higher overhead. Techniques like message queues and pipes are used to ensure the effective communication based on system needs. Fourthly, we talked about concurrency and synchronization. Concurrency improves efficiency by introducing risk like race condition and deadlock synchronization methods, which include mutex and semaphores. These two control shared resource access. And then we looked at condition variable, which enables event-based execution. We also looked at deadlock prevention, which uses lock ordering and timeouts. The last thing we covered today was design consideration for concurrent systems. Efficient systems combine shared memory for speed and message queues for flexibility or control, while ensuring mutual exclusion and deadlock prevention. A well-designed system balances reliability and scalability. We thank you.